Hi folks, we're going to take a look at number 17 from page 129. So here we have a function given for the velocity of an object. Now it's given a little differently because normally the velocity function would be given directly in terms of time. But here the velocity is given in terms of the position function. And the position function itself would be a function of time. Okay, so you can think of this actually as a composite function. But what they tell us that v is the velocity, s is the position, and they tell us that these letters b and g represent constants. Okay, so when we're taking the derivative, which we'll have to in a couple of minutes, we have to remember that these two values actually just represent some constant. Okay, so what they ask us to do is they ask us to show that the acceleration is constant for this object here given this equation for velocity. Okay, so to find the acceleration, well, what we're doing is we're finding the derivative of the velocity function. Okay, now here I'm going to use prime notation, but let's keep in mind that acceleration is the derivative of velocity with respect to time. Okay, so that's the thing about prime notation, it doesn't specify that. Okay, so we're assuming all these functions are functions of time. Okay, so let's go ahead and take the derivative. So here we're going to have to use the chain rule. So I'll think of this whole expression here in the square root as my u. So first I have to take the derivative of u to the 1/2 with respect to u. So that's going to be 1/2 times u to the negative 1/2. So that's going to be b squared plus 2gs to the negative 1/2. Okay, and now I have to take the derivative of that inside portion, our u, with respect to t. Okay, so let's do that here. So the derivative of b squared, well remember b is just a constant, just a number, so that's going to be 0. Okay, plus, okay, I have 2g times s. Now s is a function of t, okay, but 2g is just a constant. Okay, so I'm going to do the constant times the derivative of the function. So just going to have 2g is my constant, and now here this is going to be the derivative of s with respect to t. We don't know what that function is. Okay, so I'm just going to leave it as s prime, representing the derivative of s with respect to t. Okay, so let's simplify this here and see what happens. So here, well, the only thing left in the numerator is going to be our 2gs prime, okay, all over. So we've got our 2, and we've got in the denominator the square root of b squared plus 2gs. Okay, at this point here, it doesn't seem too obvious that this expression representing the acceleration is a constant. Okay, but then remember, wait a minute, what does s prime represent? Remember that s prime is just the velocity function. Okay, so v at t, if we want to think it that way, is just the derivative of the position function. So what I'm going to do now is I'm going to replace s prime, which is the same as the velocity, by this original expression. Okay, so we've got 2g times the velocity, which is the square root of b squared plus 2gs. And look what we also have in the denominator. We have a b squared, or a factor of b squared plus 2gs, and these two reduce. And in fact, so do the 2's reduce, and I'm left with the acceleration just being equal to this constant g. Okay, now likely this constant g represents the acceleration due to gravity, okay, although they don't specify that in this question here. Okay, so let's do a quick recap because there's a few different things here. So first of all, we see that velocity isn't given as a function directly of time, but of the position function. Okay, and recall that velocity is the derivative of the position function. In taking the derivative of velocity to give us acceleration, we had to keep in mind that b and g were just constants, so we had to treat them as such as we were taking the derivative, and then we recognize that in our answer for the derivative we had s prime, which is just the velocity, so we replaced my original function into the function here, and we're able to simplify.